All right, so let's look at some properties of infinite limits. Because when we looked at properties of limits before, we said that they were only to hold if the limits actually existed. So since an infinite limit is a limit that doesn't exist, I have to have some special properties here. Now these aren't properties to be memorized, but what we want to do is look at how we're reasoning why the limit is what it is. So let A and L be real numbers. And let f and g be functions such that the limit as x approaches a of f of x equals infinity. So here we have an infinite limit. And the limit as x approaches a of g of x equals L. A limit that exists. Okay, so f goes to infinity as x goes to a, positive infinity, and g goes to some value L. I don't know what the value is, but some value L. All right, so what about the sum and the difference? What if we were taking f of x and adding or subtracting g of x to it, and then taking the limit as x approaches a? Well, let's think about this whole quantity here. F is going off to infinity, and that's some notation that we often do to show where it's going when you're talking about the limit. So f is going off to infinity, and g of x is going off to some number L. So think about this whole quantity if we add them. If we add them, we've got these giant numbers coming from x, and then we're going to add L to it, so maybe 5 or -3. In the limit, remember, f of x is just going to keep getting bigger and bigger. So essentially, this L is not going to have any effect. It's going to be a billion plus 5, a trillion plus 5. So this is still going to get dragged off to infinity. And even in the subtraction case, the difference, f of x is getting so big that it doesn't matter if you take a little off of it. F of x is going to, in this sum or difference, is going to dominate over g of x and take this whole thing to infinity. All right, so how about the product? What if we take f and multiply by g and take the limit as x goes to infinity? Well, remember, f is going off to infinity and g is going off to some L. So f is getting really big, and L is some number. So we actually have a couple of cases here that we can say about, and then one that we can't. All right, so if L is some positive number, okay, and we have these giant positive numbers from f multiplying by another positive number, these are just going to be giant positive numbers. So this still goes off to infinity. Now, if L is less than 0, L is negative, then that's just going to flip the sign. Even though we have giant positive numbers, in this case, the L that we're getting is going to be negative, so these are going to be giant negative numbers, and so we get negative infinity. Now notice, I have skipped one case, L being 0. We'll get to that in a minute. We can't say anything yet. All right, how about the quotient? The specific quotient of g of x over f of x. So as x is going to a, we remember that g of x is going to some L, and f of x is going to some infinity. Okay, so one of the big things in limits is simply being able to look at a fraction and talk about what happens when numerators and denominators get big or small. We obviously know that when a numerator gets bigger, and we hold the denominator the same, the fraction gets bigger. If we hold the numerator the same and the denominator gets bigger, then the fraction gets smaller. You take 1 over 1, 1 over 10, 1 over 100, 1 over 1,000. That fraction keeps getting smaller. All right. On the flip side, if you hold the denominator steady and make the numerator smaller, you make the fraction smaller. All right, so if you have 5 over 6, 4 over 6, 3 over 6, 2 over 6, 1 over 6, that fraction's getting smaller. And what happens if we hold the numerator the constant and we decrease the denominator? So if you take 100 over 1, 100 over 2, 100 over 3, 100, I'm sorry, I went backwards. You take 100 over 100 first, then take 100 over 99, 100 over 98, 100 over 97, all right, go down to 100 over 1. Those are getting bigger now. So the idea is that a smaller denominator with the numerator the same makes the fraction bigger. So basically the effect from the denominator is reversed. Okay. So what we want to know here is, let's think about this. We've got this numerator going off to a constant and the denominator getting huge. So it doesn't even matter what the numerator's constant is, whether it's 1 or 1,000 or 5 or -3. The denominator here is going to get huge, and it's going to dominate the fraction. It getting huge is going to make the fraction smaller and smaller and smaller down to 0. Okay. Now, we definitely skipped a lot of possibilities there. And if you remember before, we had the 0 over 0 situation, which we called indeterminate. Indeterminate. Well, there are a lot of other indeterminate forms besides this 0 over 0. Now, I put quotes around these because it's not actually that you're doing 0 over 0, because you can't. And in this first one here, it's not actually that you're going to subtract infinity from infinity. It's just notation. Something going to infinity minus something going to infinity. We cannot say that's 0. All right? These are all going to be indeterminate. And there are ways to work around them, as we'll see. Same thing for infinity over infinity, and something going to infinity times something going to 0. Again, something going to infinity and going to 0, because you might say, oh, isn't anything times 0, 0? Well, it's going to 0. And you've got something, so in this last one, you've got a battle going on between something that is trying to get huge, multiplying by something that's trying to get to 0. And it can end up being anything. It can end up being infinity. It can end up being 3, 8, 1/2, -7, or negative infinity, or it can be anything. It all depends on how it's going to infinity and how it's going to 0. So again, these are all indeterminate. We can't make a distinction just from that form. We need more work on it.